Hi everyone, and welcome to this video, which I wanted to make as I reviewed some notes on complex analysis and dynamics from the previous year about attracting cycles of rational maps. And I'll explain the basic setup of classical complex dynamics and how we can use a beautiful result in hyperbolic geometry to derive behavior of iterated rational maps on the Riemann sphere. So the basic setting is as follows. I'm denoting the Riemann sphere by C hat over here, and F is going to be a rational map of degree d greater than or equal to 2. Recall that the rational maps are exactly the meromorphic functions from the Riemann sphere to itself, among which the rational functions of degree 1, the Mobius transformations, are the automorphism group. Now, the degree is the greater of the degrees of the polynomials that you take the ratio of when defining the rational function, and it also corresponds to the topological degree of the map. So here's the hyperbolic geometry that I wanted to talk about before diving into any of the dynamics, and it comes in the form of the Schwarz lemma. In many complex analysis courses, you see the Schwarz lemma presented in a certain form as a fact about maps on the unit disk in a complex plane. And this is a special case of a much more general and beautiful fact which you can phrase about hyperbolic Riemann surfaces. So first, let's recall that we have the uniformization theorem, which of course I won't prove in this video because it's quite long, but this beautiful result which says that every Riemann surface has universal cover, one of three Riemann surfaces, which are simply connected, right? These are the Riemann sphere, C hat, the complex plane, or the upper half plane, which is isomorphic to the unit disk. And we refer to a hyperbolic Riemann surface as one which is covered by the upper half plane. Now, we can phrase the general form of the Schwarz lemma, this is sometimes attributed to Schwarz and Pick, or sometimes Alfor's name is attached to this, as having to do with the canonical hyperbolic metrics that each of these hyperbolic Riemann surfaces inherit by being covered by the upper half plane. So because the automorphism group is exactly the orientation-preserving isometry group for the hyperbolic metric on the upper half plane or the disk, each such hyperbolic Riemann surface inherits a hyperbolic metric of constant negative curvature minus 1, and we refer to these as the hyperbolic metrics on the respective surfaces. So we're going to let F be a holomorphic map between two Riemann surfaces that are hyperbolic, x and y, and the Schwarz lemma in this generality states that every such map is non-expanding for the hyperbolic metric. So this means that the distance between f of x and f of x prime, where x and x prime are 2 points in x, is less than or equal to the distance between x and x prime in Riemann surface x. And you can also phrase this by saying that the differential of the map between tangent spaces is has norm less than or equal to 1. We can phrase this in the form of the following dichotomy. So either f is a contraction for the hyperbolic metric, where you have strict inequality, right, where it's decreasing distances, or equality holds, in which case it's a local isometry. And this turns out to be true if and only if f is a covering map. Okay, so now this is our setup. And I want to also talk about one tool in the theory of proper maps between Riemann surfaces, or if we'd like, since we're only dealing with the Riemann sphere, a theorem about compact Riemann surfaces. And let's say x and y are compact Riemann surfaces, and we have a holomorphic map f between x and y of degree d, let's say. Then the Riemann-Hurwitz formula relates the genus of x, the genus of y, the degree of the map, and this error term, which is basically factoring in the ramification. So this topologically corresponds to the branching that happens because every holomorphic map between Riemann surfaces is locally a covering map of some fixed degree. So in this case, since we're dealing with the Riemann sphere, first of all, we know that the source and target, of course being the same Riemann surface in this case, both have genus 0. And in this case, since we have simple branching of the generic case, the error term over here, the sum on the right-hand side, is simply counting the number of critical points. So this tells us that a degree d map from x to y, the Riemann sphere to itself, is going to have 2d minus 2 critical points, which formalizes some fact that we might know otherwise. Okay, now it's time to start talking about some dynamics. The basic setup for holomorphic dynamics in one complex variable is that we have a rational function, typically of degree greater than or equal to 2, on the Riemann sphere, and we study its iterations. and the iterations applied to a point, that's called the forward orbit of the point. And you can also form a geometric theory by studying sets like the Fatou set and the Julia set, and so on and so forth. So the dynamics of such a rational map are controlled by its attracting cycles. Specifically, well, I would say that it's critical points, and we're going to give a bound on the number of attracting cycles that a rational map of fixed degree can have. Now, looking at the size of the first derivative at a point tells you the kind of local behavior that this map has, whether it's locally attracting, which means that the size is less than 1, expanding greater than 1, or if it's neutral or indifferent, where it's equal to 1. So this local behavior, by taking a Taylor series expansion, tells you the kind of activity that's going on in the neighborhood of a point. So with this heuristic in mind, we said that a collection of points a1 through an, in that order, is an attracting cycle for f if f cyclically permutes them, and such that the size of the derivative of the nth iterate at a1, this first point, is less than 1. So it's pulling in points in a neighborhood. So it's easy to see that there exists some open neighborhood around this attracting cycle that over time, upon iterations, are going to converge or go in. And this neighborhood is called the immediate basin. So we're going to prove the following result, which is that any attracting cycle of f, let's say a rational function of degree d, attracts a critical point. And as an immediate corollary, since we know that the number of critical points for a rational map of degree d is 2d minus 2, this tells us that there are at most 2d minus 2 attracting cycles. Okay, so let's go through the proof. By replacing f with its nth iterate, we can assume, so the first point has period n, we can just replace with the nth iterate and just assume that there's one point in the attracting cycle. Let's call it a. And let u be the immediate basin, and in case it's not connected, let u naught be the connected component that contains this point of the attracting cycle. Now the key point is that since we have a rational map restricted to some open subset of the Riemann sphere, a compact Riemann surface, the restriction of f to this neighborhood u naught is actually a proper map. This means that it pulls back compact sets to compact sets, and the theory of proper maps between Riemann surfaces is a very rich one. Now, under the assumption that f has no critical points in u naught, then it'll be a local homeomorphism. By a general fact, any proper local homeomorphism is a covering map. So the restriction of f to u naught is a cover. And this is equivalent if we assume that u naught, the complement of u naught has at least 3 points. We can deal with the other cases separately, but they're not as interesting or general. This occurs if and only if f restricted to u naught is an isometry for the hyperbolic metric, as we saw with the Schwarz lemma. But this contradicts the fact that the multiplier at the point a is less than 1. Hence, f must have a critical point in the neighborhood u naught. And this immediately proves our claim. So thank you for watching this video. Hopefully I'll try to augment it with others on complex analysis or dynamics, which I find a wonderful area of study that I've been fortunate to learn a lot about recently. And yeah, that's all. Thank you for watching this.